The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, I'd like to introduce Mark Burry as our final but speaker for tonight. Mark has been with BASF for 28 years. He's responsible for the strategic development and management of Master Builder Solutions brand admixture products and concrete technologies. Mark has authored over 30 papers and has multiple patents on freeze-thaw, durability of concrete technology, and a corrosion inhibitor admixture. The one that grabbed my attention was that Mark has led the program of researching concrete performance and microgravity experiment in outer space aboard the Space Shuttle Endeavour. So that would be me, a space nut. That was good. So Mark is a fellow at ACI and a member of ASTM and has accepted an appointment to section chairman for the chemical admixtures CO9 2330. So Mark, it's all yours.
Thank you, Rick, for the nice introduction. Good evening, everyone. Thanks for having me. I can back clean up here and kind of finish up this session. It's pretty interesting. I'm pretty excited about it, hearing all the different viewpoints about the whole 90-minute rule. And what I'd like to do is just share with you a little bit of information about extending, concrete slump life and then proven technologies that we've worked with in our industry over the last really 30 plus years, projects with challenging placement. So I'm going to break this down into 4 real easy categories here. We'll talk a little bit about concrete slump loss, maybe where some of this 90-minute rule came from. We'll talk about workability retention and the options we use within our industry, some of the admixture solutions and impacts, and then some projects. I think you'll find those pretty interesting. So let's start with slump loss a little bit. So in the upper right-hand corner, we start with batching and mixing. We're adding water to Portland cement at the batch plant, and all the surfaces of the cement grains are exposed to water, and then they start to hydrate. And as they start to hydrate, that leads to flocculation and loss of workability over time. So this graph here is simply meant to show you this is a typical concrete mix starting out at whatever slump you want to originate at, 5-inch, 8-inch. That would represent your 100% workability. And then over time, you're going to lose that slump, or you're going to lose that workability. And then there are all kinds of factors that will affect how fast or how slow that slump loss is. So the slope of that line would change as your materials change. Are you using a real rapid setting cement or a little slower setting cement, a little slower reactivity cement? What is the production time and the transit time through the job site? And the environmental factors. What is the temperature of the concrete itself? What is the ambient temperature? All those things will change that slump loss. So let's rethink this 90 minutes here for a second. I think what Terry showed earlier was, in his opinion, it was an unnecessary limit. And some of the reasons were already shared with this group, but it's like, what is a producer to do if they have a project that's specified that's a very long distance away from where that concrete's being batched? What is a producer to do if traffic or weather conditions really slow up, the batching to the actual delivery and placement of that concrete? And what about the application? And this is just one of maybe several applications, but drilled shafts, for an example. You're batching the concrete, and then you're mixing the concrete to make sure it's good and homogeneous, and then there's some transit time. And then when you get to the job site, there's positioning that truck to the pump, And let's say, for example, we're using self-consolidating concrete for a drill shaft. It's a very fluid mix, but maybe the discharge is a little slower to make sure everything gets consolidated. And then there's multiple trucks positioning themselves because we don't want to get any cold joints in there. So you could easily exceed 90 minutes in some applications. This is just one example. So what does the industry do? What do we do as an industry to counteract slump loss? Well, we can retemper with water. That's late addition of water. We can batch higher than required slump. And that one's a little bit scary, but I'll show you a little graph on that. We can use chemical technology in the form of a retarding admixture. We can use a high-range water reducer and redose with that. We could use an extended set control, or also known as hydration controlling admixtures, or a workability retaining admixture. So we have lots of options that we've dealt with over the years to counteract slump loss. On the admixture side, a retarding admixture is nothing more than an admixture that decreases the rate of hydration. And as a result of that, it can lengthen setting time. An extended set controlling admixture is a little bit different. It functions by literally stopping or significantly retarding the hydration of Portland cement. And it also thereby lengthening the setting time. And a workability retaining admixture will provide workability or slump retention when used in combination with normal or mid-range or high-range water reducers without affecting the set time. So there's a distinction between a extended set control and a workability control. One will affect set time, the other one will not. And we're going to see how all these come into play in some real-life projects. So let's take a look at this little chart. The source was the FHWA, and it simply shows stages of cement hydration because it'll help to illustrate how these things work. So we have an initial heat rise when water comes in contact with Portland cement, and then that's stage 1. Stage 2 is the dormancy period. There's not much going on. You don't have any heat being generated, and it's in that phase or that stage, if you will, as to where the concrete remains pretty much plastic, and you have to do all the processes to get that concrete batched and mixed and delivered to the site and placed and consolidated with vibration and finished before your C3S starts to react and you start to get heat generated again in stage 3. And then you have a cooling effect in stage 4, and you get strength gains starting in stage 5. But I think it's interesting that we look at this because that's where this stage 2, for example, which on average typical lasts about 2 to 4 hours, depending on your mixes and conditions. But that's where you find your slump life and your workability retention in that dormant period. So that becomes a focus. So let's look at a retarding admixture for a minute. Those slow the hydration of cement and concrete. And that rate of slump loss may be decreased, and the working time can be extended. That's found in the ACI 212 document on retarding admixtures for concrete. They meet ASTM C494 types for type B is a retarding admixture, type D, which is water reducing and retarding, and type G, water reducing, higher range and retarding. I don't think we see in our industry many of the type Gs anymore. They've pretty much been phased out of the industry. But these are typically used when it's warm outside. And you're going to get more slump loss when it's warm, and these are designed to retard the hydration of Portland cement when it's warm. And you can see in this graph, and this is a heat evolution graph, the plain concrete that's untreated, no chemical technology in there, has this little dormant period from the 2 to 3 hours. It's in the blue. And when you put a retarding admixture in there, it simply shifts that heat curve to the right, simply making that dormant period much longer, nothing's happening, slump life. So retarders are used fairly regularly in our industry for some slump life. I'm sorry? Because it's a water reducer. You can have a water reducer that retards as well at elevated dosages, but this was just for the retarding admixtures. Yeah, good question. The hydration controlling technology is a little bit different. This is an industry innovation that came on the market in 1987, so we're talking 31 years ago already. It effectively puts concrete to sleep. It stops hydration. It works both on the silicate and aluminate phases, which is a little different than retarding admixtures. It forms a protective barrier around the cement, and over time that effect dissipates, and when that dissipates, the barrier breaks down and then concrete starts to hydrate as normal again. So just graphically, if you see the little cement grain here, when you put one of these chemical admixtures in the concrete, it forms a physical barrier around the cement grain. So water's not getting to it, you're not getting hydration. Over time, that will dissipate. And when that dissipates over time, then you have normal reactions that start occurring when the cement grains, are exposed to water again and cement begins to hydrate again. And that normal hydration and setting and strength will occur after that barrier breaks down. The more chemical you put in, the more robust the barrier, and the longer you can keep that concrete fluid or plastic. And it meets the criteria for ASTM C494 for a type B and a type D admixture. Here's the same heat curve, if you will, except the extended set controlling admixture was added to this, and that's in the pink, to show you that it can put concrete to sleep, no hydration for as long as you want. Obviously, in the real world and for practical applications, you can delay this as long as you want, but it becomes economically unreasonable or unviable if you want to keep it to sleep for a day, 2 days, 3 days. It can be done, but it's, there's no reason to do that. But it's designed here to show you the difference in the heat generated because there's nothing happening. Now, one of the more recent innovations, 2006, that should be 16, I believe, or was that 6? Yeah, it was 6. Well, workability retaining admixture. These are added at the batch plant, and the effectiveness is based on the dosage, and it maintains concrete slump and workability over time. And here's some little pictures as an example. So if you take an 8.25 inch slump concrete, it's got a 3 fluid ounces of a water reducer in there, it'll lose over 90 minutes, ambient conditions, 5 inches of slump, 4.5 inches of slump. You take the exact same mix, same conditions, and you add 4.5 ounces of a workability retainer, and you start out at an 8.25 inch slump, and you end up with an 8 inch slump 90 minutes later. The difference here in this between the others is there's no effect on early strength or set time. So it's a much different technology to keep slump alive, keep workability good without affecting your strength or early set time. So it does not retard, does not affect early strength, and it will meet the ASTM C494 criteria for a type S admixture. And here's an example of some data that shows the differences between the hydration control and the workability control technologies. If you have a setting time here of a little over 6 hours with a reference mix, you can keep the workability by adding a hydration stabilizer, but you're going to affect your set time. It's going to go up a little bit. So you can maintain your slump, but your set time will be affected. When you add the workability retainer in the green, you can extend your slump life and you won't affect early set time, initial set time. So there's the distinction, there's the difference. Both of them have their uses in practical applications, which we're going to talk about now after we look at some of the effects these have on concrete properties. So let's just look at this graphically for a minute, and this is just designed to give an illustration of what happens. Actually, slump loss is not linear like this. There's a little bit of curvature to that. This is just for illustrative purposes. If you do nothing to the concrete, you're going to lose slump over time, regardless of what your initial target was. You can add water. After you lose so much slump, you want to get that slump back, you add water, retemper the concrete, you'll get some slump back, and then it's going to lose slump over time again. And you can do a similar exercise with on-site additions of super plasticizers, where you lose some slump, add some super P on the job, get your slump back, and then it's going to lose slump over time. Or this is kind of the scary one, but I know it's done and people do it, sometimes successfully, but that's batching way more than you need and hope you get to the slump that you want at the time you want at the job site. That one's a guessing game, and It's done successfully sometimes, and people really know their materials and their delivery, but that one's a little bit sketchy, in my estimation. Those were the three that we dealt with for quite some time. With the advent of the workability retaining admixture, this is what we see in terms of slump retention. Over time, the solid line is at a low dosage. So you'll see pretty much control slump for some time, and you'll see just a little bit of tail off, a little bit of loss of slump. And at higher doses of this material, you actually get a little bit of slump gain over time, and then it'll eventually tail off. But this begins to show you there's a magnitude there where you can really deliver concrete to some remote locations without changing the slump or the early setting time or the strength at all. Conversely, with the hydration stabilizer or the extended set control admixture, you can flatline it for as little or as long as you want. Again, the solid line is a low dose, so it shuts off hydration, and then you'll start to lose some slump as that barrier that I showed you dissipates. Or with the high dosage, you can shut that hydration off for a long period of time, and then you'll get slump loss when that barrier breaks down. So let's look at these slump life options and what happens to the properties of concrete after the fact. So here they are listed, from retempering to batching higher than required, redosing with supers, retarders, extended set controllers, or workability retaining. So the effects on slump are shown here. Just for an example, you retemper with water, you're going to restore the slump. And these other options either minimize the slump loss or maintain the slump. What's interesting, though, is what happens after the fact. So if you retemper with water, you'll restore the slump, but you'll also have a delay at the job site. You'll have variability in air content because slump and air are intertwined. So you start adding water, now what happens to your air? You'll delay your setting time, you'll decrease your strength, especially at early and late ages if you're adding water, and you're going to increase your drying shrinkage. The bottom line is, when you look at this graph, I tend to put these in groups. If you look at those first four options, there's a lot of X's, which means a lot happens to your concrete properties. It's easy to see that using some of the extended set controlling admixtures or the workability controlled admixtures don't have many serious effects on the concrete properties. So those might be the way to go if you're looking at not changing what you want to get out of your concrete in terms of performance, whether it's plastic or hardened concrete performance. Let's take a look at a few projects in practice here. And what I tried to do is mix this up for you a little bit. There's a couple of old ones from the 80s, some in the 90s, and a couple from the more 2000s, just to give you a flavor for how these are used in the industry. So this was a project, a microwave tower, footing foundation. U.S. Department of Energy was the owner. This was Monument Valley, Utah, but the ready-mix supplier was in Flagstaff, Arizona. So there's a picture, and the two little white dots you see in the middle of the desert here are concrete trucks. And so they're a long way from the batch plant, 8 hours away, 250 miles away. So here's pictures of the concrete trucks driving through some pretty ridiculous terrain, no paved roads, desert, going in the middle of nowhere to place this footing foundation for a microwave tower. And actually, I was told that the drivers actually discharged the concrete and finished it when they got there. There weren't any contractors on site. But you can see the rough terrain. I missed the picture. I was going to throw one in here. The truck drivers were actually avoiding wild horses that would just run across right in front of the trucks, and they were trying to avoid some of the wild horses out here. But 8 hours away, 250 miles. That's quite an event. How about this project? This was the Nebish Light Cell, U.S. Coast Guard navigation system. This was part of the Great Lakes communications area. St. Mary's River, Sault Ste. Marie, Michigan. Northern Sand and Gravel was the producer. 210 yards, about 64 to 82 degrees were the ambient temperatures for this job. The key was, or the challenge here was, this was an underwater concrete placement. So it was a base seal slab, cobblestone base, concrete on top, anti-washout admixture to keep the concrete from washing out underwater. hydration controlling admixture at 11 fluid ounces, 50 yards of concrete. But the transit from the batch plant to the barge, loaded on the barge to the site, we're talking one way, 12 hours. Again, you have to do some manipulations to the mix design, use some chemistry to get 12 hours of very good slump. When you do underwater concrete, you also is typically pumped or chummy placement. It has to be high fluidity because there's no vibrators underwater to consolidate the concrete. So it has to be pretty high fluidity. So with this particular job, great flowing characteristics. I believe the design strength was 5,000 PSI. We're getting 6,800 plus PSI on this particular job at 28 days. So underwater concrete is where you could use these types of technologies. It was mentioned earlier, One World Trade Center, New York City, Manhattan. The engineer says, I would like 14,000 PSI at 56 days, and it has to be over-designed, 1,900 PSI for safety, and I want the modulus of elasticity to be 7.25 million on the modulus. Heat of hydration cannot exceed 160 degrees Fahrenheit, and I don't want it air entrained because we're looking for high early strength for the building. But the Port Authority says, okay, that's fine, but we want it to be sustainable. You can't use more than 400 pounds of Portland cement in your concrete mix. And then now we have to look at the contractor. The contractor's got their own set of criteria. The contractor says, yeah, but I want the slump flow to be 24 to 28 inches, and I want to pump it 100 stories straight up, and I want no loss of workability, and it's got to look good at the end. So there's all your criteria. So what do we do? And by the way, it's batched in New Jersey and driven to New York, so we're batching it a state away. Summertime and wintertime through Manhattan traffic. So very routinely, more than 2 hours of haul time here, self-consolidating concrete, and it was able to be accomplished very nicely. Here was the interesting part about this project. It was a combination of the workability retaining admixture and the hydration control admixture. We're pulling levers here based on what the engineer and the contractor and the owner wanted. So I think somebody asked before, if I'm an engineer, how do I specify all this stuff? It's a great question. We're finding you specify what you need and want for the project, and the material scientists from some of the admixture companies and the really good producers that we have for these kinds of projects, we'll figure all that out. But tell us what kind of engineering performance you want and the parameters, and we'll have a discussion. We'll do mock-ups, and we'll make sure it works. In this case, it worked great. It actually won Green Site Project of the Year. All the performance requirements were met in terms of the strength and the modulus, and all the environmental factors and the environmental footprint was what won the Green Site Project of the Year. So we were able to reduce energy, reduce CO2, save on ozone depletion, CO2, water emissions, solid waste, land use. All that was quantifiable savings by using these kinds of optimized mixtures with these chemical technologies. Another project, U.S. Courthouse. Let's move from the East Coast to the West Coast now. This was, I believe, L.A. white cement. So the white cement in this application, very reactive, acted like a type 3. Ambient temperatures in the morning, 70s and 80s degrees. End of the day, you're talking 90s and low hundreds. 5-inch slump, design strength 4,000 PSI, more than 2 hours of transit time. Slump was maintained without any additions of water, and the extended hydration control admixture was used on this project. Really nice looking building, outstanding looking. Fresno? Thank you. How about this one, William Moore Bridge? This is in Alaska. So we're talking about roller compacted concrete, 12 inches thick. Under the bridge is a access road. The requirement the engineer wanted for the project was, I want hydration stopped for 14 hours, 10 ounces per hundredweight of the hydration controlling admixture. And they wanted it stopped because it's a long haul to this site. And then they had challenging placement. They had 3-yard buckets lowered by crane into the canyon. Here's a little picture of that. and then they lowered the roller compactor to the bottom to kind of roll it out 23,000 yards. But here you're talking about stopping hydration for 14 hours. So trying to give you a little flavor for all the different ways these things can be used. This one is actually the MTO in Ontario, Canada. Long haul applications, especially northern Ontario, from the batch plants. The placement requirements, concrete must be plastic, greater than 3 hours after batching. There was a durability study done on all these types of concretes with compressive strength, with air void parameters, with freeze-thaw durability, with scaling. The concrete here exceeded all the performance requirements, and as a result of this durability study, the MTO in Ontario said that the concrete, being delivered to these more remote locations had to have a workability retaining admixture, and it was approved for these long hauls, and it meets the ASTM C494 Type S specifications. This is a picture of it being used in a mine and some tunnels in northern Ontario. It's also used, in addition to that, on bridge decks and other applications. And I had a video and it kind of disappeared, or maybe we can go back to it. And the last project here I'll share with you is Fisher Island. This is in Miami, 15,000 cubic yards, 500 cubic yard pours, 5-minute spacing, 3,500 PSI. No job site water was allowed. You can't start between or after or before 7 a.m. usually. In Florida, it's cool early, it gets warm later, so you want to start early, but in this case, there was a constraint there. 20-minute travels to barges, 30-minute barge trips, 3 trucks on a barge, wait times, 98-degree ambient temperatures, and I believe some of the initial work that was done were without any measures taken for some of the slump loss. And so there were 4-inch slump loss in transit. It wasn't pumped very easily vertically. Pumping was clogged, cold joints, 12 to 15% of the loads were lost. 2-hour round trips to the dump, inconsistent set times, and flash sets. So the answer was workability retaining admixture. All the slump losses were eliminated, pumping issues eliminated, cold joints eliminated, lost loads, rejections, trips to the dump. So these technologies can be used to give concrete good slump life and really good engineering properties. And we have really good producers out there like Titan and others that can do these things. It shouldn't scare anybody anymore. So in summary, concrete can be placed well beyond 90 minutes. We've been doing it now chemically for more than 30 years. The technology that can control slump life are the set control admixtures, extended set control admixtures, workability retainers. We can maintain the engineering properties, and virtually every application you can think of, these are viable candidates. We've done it in everyday concrete, long hauls, traffic, weather conditions, underwater, sustainable concrete, fast settings, cement concrete, high performance concrete, SCC, roller compacted concrete. The concrete itself doesn't know where it is or what it's doing. It's Portland cement, water, and aggregates, and some admixtures. And if it's proportioned right with the right levers of tweaking some of the chemicals in there, we can do things before 90 minutes or well after 90 minutes and maintain the properties. So with that, I'm happy to answer a question or two.
Thank you very much.
Sure, thank you.
Appreciate it very much.
Mark.
Yeah.
Okay, so you can make concrete last for 4 hours, but what criteria would you use to reject the truck after 4 hours? Like, you have the QC guy out there in the field. What's he going to use for the criteria?
I'm not sure you would reject it for a time constraint.
The question was, if he says he can make the concrete survive for 4 hours, what does the QC man in the field use to say the truck is good or not good?
90 minutes.
90 minutes.
Hey.
in that position, what's the only measure of workability we have right now? There's two of them. What are they? Slump or spread. Air doesn't measure workability. Slump or spread, depending on how the concrete is designed and where it's going to go. If you've still got your target slump and you've had a pre-con and you have agreed upon what's your starting slump and what loss you're willing to suffer, okay? All concrete loses some slump. If you've agreed on that, now you're an hour later, you're 2 hours later, you're 3 hours later, you still have your slump and you haven't added water. As Colin said, you don't add water. And then someone made the observation about measuring temperature. You want to measure temperature? There's your two tools, temperature and workability. Done.
Other questions?
I think it's sort of misunderstood that 90 minutes is some gospel to it. I think the intent is saying that the purpose of the C94 revision is the purchaser gives the ready mix producer a better understanding about the intended delivery time of this mix. And if you say it's 4 hours, that's the basis by which you reject it. But you still have the ability to waive it if the slump is okay. The main thing that C94 is worried about is that you haven't exceeded the water from the mix design, because at that point you detract or degrade the quality of the concrete. And I don't think time is of essence here. It's not the criteria. Basically, C94 is very thing about you should not exceed the water in the mix design. That's the main criteria that is the basis for what C94 is worried about. And 90 minutes doesn't make any sense because a curb and gutter mix will probably go south in 30 minutes if it's 90 degrees out there. And if the producer doesn't know that they're going to take more than 30 minutes to thing, then they're going to add water to it and it's going to go, detract the quality.
I just want to give my thoughts about this presentation and I'd like to hear some feedback. What we seem to be talking about is two different kinds of concrete. One is that we know ahead of time that it's going to be requiring more than 90 minutes to place that concrete, whether it's 14 hours, whatever. We've done that before. And in my experience dealing with structural engineers and owners and what have you, if we know about it, we talk about it, explain to the engineer that why you need to exceed 90 minutes, whether because of travel distance. Hey, I've never had any project where that happens where the engineer said, nope, absolutely, you got to go with 90 minutes. The 90 minutes that we're dealing with is really more of everyday concrete. Nobody tell you, contractor are not going to tell you that, hey, I'm going to hold your truck for over 90 minutes because of whatever. I got a difficult pumping situation, I have whatever. So I think that there has to be some, with that type of concrete, I didn't anticipate that you're going to take that long. I'm assuming that it's a normal travel time of maybe 30, 45 minutes, get to the job, contractor 10 or 15, 20 minutes, and that truck is empty and it's coming back. Now, the research at the university is a wonderful data. The one thing that is not mentioned, though, is that this redosing of admixtures and all this, you're doing something to change that property of that concrete. And if you present it to a structural engineer that's what you're doing, that you're going to have somebody redosing the trucks with chemicals and not water, I think a reasonable engineer is definitely going to accept that, yeah, you can definitely go over 90 minutes. But when we're talking about this redosing of admixtures and what have you, and having a QC person or somebody doing that, let's not forget there's a cost involved, okay? Somebody, if I as a producer, if you as my customer or somebody's willing to pay for that extra admixtures that I didn't budget in my bid when my sales guy go out and sell the job, he's telling me that, hey, it's normal mix. And if I would have to required to post a QC technician and add all this admixture somehow, that's additional cost that we didn't figure into our bid. And so there's a cost component involved. So, and the bottom line is, I guess, 90 minutes goes away very easily if there's prior communication that there's legitimate reason to go beyond that. I don't think any engineer will deny that. But if it's just everyday concrete, I think we got to have 90 minutes there so that the truck is not set on the job and gets stale very quickly after that.
So, Tack, I think, if anybody can't hear me, let me know. I think that's a really good point. And as I mentioned earlier, how many people in here have seen where concrete didn't last 90 minutes before rapid slump loss? Okay? So, in reality, by looking at maybe this change, what that does is that improves the conversation between contractor, engineer, and producer as to what the expectations are. So everybody's expectations are met. And so on a lot of jobs, if you have 20-minute haul, 30-minute haul, and it's off the truck in 10 minutes, if your concrete lasts 90 minutes, great, or 50 minutes, you're good, and the producer will have an idea about his materials. And if it's longer, that forces that discussion, or not forces, but encourages everybody to have that discussion, and therefore jobs are going to run smoother. And if it costs more, then you're having that discussion up front about what is needed for that project, and it's addressed then instead of later.
Well, what I will add to that, especially with regards to the redosing concern, is that keep in mind, it's a research. Our aim is to get to the optimum dosage rate, continue the research and see what works. So we are getting there. We haven't quite gotten there as yet. So naturally, you're going to have trial and error, which is the stage where we're at. So yes, we had a redosing of the Super P and the air, but we are determining the optimum dosage rates to achieve the particular results. So we will get there, and those are the steps that have to be taken to get to that stage. So when you're developing a mixed design, more often than not, you're not going to get it right on the first try. And that is pretty much what we're doing, working towards that goal, where we determine ahead of time and be able to present more consistent facts and data of optimum dosage points, dosage rates, etc.
Okay, I've got a comment. I'm out of New Mexico, and I was in the ready mix business, and all of our concrete for the I guess I started researching this 40 years ago, before we had a lot of admixtures. But we got to the point where we trained our drivers with thermometers to watch the temperatures, because our average haul was probably hour and a half to just get there every day. And then as we got involved with, I'll use the admixture number, but it was 300R. And if we had to go over 2 hours, we'd add 300R. And we found out that if we loaded the truck and it left at about a 5-inch slump, and we did 1 revolution per mile to keep the heat of hydration and the heat of the friction between the particles reduced, we didn't have an increase in temperature. There were some jobs that we had with the Bureau of Indian Affairs, and we delivered concrete 2 hours. It left the concrete plant at about close to 80 degrees. And 2 hours later, we got to the job site. We had to go over a hill, a summit as we called it. Everybody had to turn their heaters on. We got to the job site, and all the concrete was at about 70 degrees. We had a drop in temperature driving down the highways with the metal drum, which in turn cooled the concrete in the drum, which allowed a higher slump. And everybody says, I've never heard of this. Well, this has happened and we monitored it all the time. But I'm for getting rid of the 90 minutes. And as a former producer, I had no problems delivering it to people. And like I would tell them, if it's starting to get hot and you're having to add water, add the tank water that's in your truck, or carry 10 pounds of sugar with you, and and get it out of there, but don't use it in a job, because if it's getting too hot, just stop it. Just say, this is gone to hell. That's all. And I think getting rid of the 90 minutes, I'm for it, because I think as a small ready-mix producer that we were, there's no problems delivering quality concrete with all the new admixtures. Because I think in the last 20 years, we've increased the admixtures 200% from what we had 40 years ago. That's my comments.
Rather than dropping the 90-minute rule, what's wrong with changing some of the terse language from shall to more performance-based material language? If we are using these chemistries, we may extend the time with SCCs, the proper chemistries. Could we do that with C94? Is that possible to remove the terse language?
Well, I think some of the language already has that.
Yes.
And people only get hung up on that first part.
Yeah.
So, and that's been that way for a while. So I think we really need to move to the next step to get people to go beyond that. And so what they've done, I think, if I'm correct, is they've moved that language down below as a footnote of the history. Mm. And they've changed that language to get people from just focusing on that.
Thank you.
Yeah, I think your point's well taken. The mandatory language is typically right in the body of the ASTM methods, and the non-mandatory is in the footnotes. But maybe there should be some more footnotes to that effect, exactly what you're suggesting.
I think they had some.
Yep.
Okay, well, thank you, everybody, for attending. We really appreciate the attendance. Have a good night.